in this video, we take a look at the second order partial derivatives. So again, if you remember back to single variable calculus, you can repeatedly apply the derivative to get higher order derivatives. Right? So like for example, the derivative of the first derivative is the second derivative, and if you take the derivative again, you get the third derivative, and so on and so forth. So we can sort of do the same thing for partial derivatives, but because for partial derivatives you do it separately for each variable, you can mix and match the different partial derivatives in different ways. So for a function of two variables, there are four different second order partial derivatives depending on which order you apply them. So for example, if you apply two consecutive partial derivatives with respect to x, you get this. So typically it's written as d squared f dx squared, right? So this second power notation implies that the derivative with respect to x is applied twice. And so if you prefer the subscript notation, is written as f sub xx. So here again it means that the partial derivative with respect to x is applied twice. If you apply the partial derivative with respect to y twice, then this is the notation. So the one you want to be careful about is if you have the mixed partial derivative. So if you take the partial with respect to x first and then with respect to y, then this is the notation here. So when you write the notation like this, you work inside out, right? So basically you read from right to left. So this means the partial with respect to x first and then with respect to y, right? So here from right to left with respect to x first and then with respect to y. However, if you're using the subscript notation, the order goes the other way around. So in this notation, you read it from left to right, right? So the x first and then with respect to y. So you notice how the ordering of the x and y is the opposite in these two cases, because again, this notation on the left, you read it from right to left. This notation here, you read it from left to right. So similarly, if you do it the other way around with y first and then x second, then the d notation looks like this, and then the subscript notation looks like this. Again, so the note here is just saying be careful whether you use the d notation or the subscript notation, to pay attention to the order that you should apply the partials in. So this is y first and then x. This is y first and then x. Okay, so the lucky thing is that in most cases, it doesn't matter whether you do it this way or this way. So theorem 3.1 says that if the two mixed partials are continuous around a particular point, then whether you do x first and then y, or you do y first and then x, the two mixed partials are the same. And so it doesn't matter whether you do it this ordering or this ordering, you should get the same for most functions that we deal with. Okay, so with that in mind, let's take a look at an example where we calculate some second order partials. So here in example 4, we're given this function and we're asked to calculate these three second order partial derivatives. So as always, you apply the derivative one at a time, right? So before we can calculate this second order derivative, we need to calculate the first order derivative. So the first order partial with respect to x. So here I treat y as a constant. So this expression, again, you have the xy sitting inside the cosine function. So this requires the chain rule. So the derivative of the outside, derivative outside is cosine, derivative of cosine is minus sine. The inside stays the same, and then I multiply the derivative of the inside. So y is being treated as a constant here, right? Because I'm taking the partial with respect to x. So this is just a coefficient times x. So the derivative is the coefficient, which is y. Okay, so here we're differentiating with respect to x. So this is just minus 3x squared. And then here I'm treating y as a constant. So this whole thing is just a constant, and the derivative of a constant is equal to 0. Okay, so this is what I get for the first partial with respect to x. And so let's rewrite it. So typically something like this, I put the y in front of the trig function. So you get minus y sine of xy minus 3x squared. Okay, so now that I have the first order partial with respect to x, then I can now get the second order partial. So here I take this result here for the first order, and then now I have to take another derivative with respect to x. So I'm treating y as a constant for this thing. So this is just a coefficient, so the derivative doesn't affect this. And then here I have to apply the chain rule. So the derivative of sine is cosine. The inside stays the same, and then times the derivative of the inside. So y is the constant, so this is just a coefficient times x. So the derivative of the inside is y, and then here I need to differentiate this with respect to x. So I get minus 6x. Okay, so now we just simplify. So y times y is y squared. So you get minus y squared cosine of xy minus 6x. Okay, so this is the partial with respect to x done twice. So now let's do the mixed partial with respect to x and y. So I have to use this one again, and now we calculate the mixed partial. So I have to look at this, and I'm calculating the partial with respect to y now. So I'm thinking of x as the constant, so y is the variable, right? So here I'm going to have to apply the product rule, right? So because this contains a y and this also contains a y, so I apply the product rule here. So the derivative of minus y is minus 1, and then this part stays the same. And then this part stays the same, so minus y times, and now I differentiate this part, and that requires the chain rule. So derivative of sine is cosine, the inside stays the same, times the derivative of the inside. So I'm differentiating with respect to y, so x is the constant coefficient, so that comes out. Okay, and then here I'm treating x as a constant, so this whole thing, the derivative of constant is 0, so this whole thing goes away, and so this is what I get. And let's just simplify. So you get minus sine of xy minus xy cosine. Oops, I'm kind of running out of space, so let me write it just below that. So minus xy cosine of xy. Okay, so that's what I get for the mixed partial. And so finally here I apply y twice. So I need the first partial with respect to y first. So what do I get here? Derivative of cosine is minus sine. I'm applying the chain rule, so the inside stays the same times the derivative of the inside. So x is the constant coefficient. Here, this only contains x. I'm treating x as a constant, so derivative constant is 0. And here, this is just the ordinary derivative, so plus 4y cubed. Okay, so I get minus x sine of xy plus 4y cubed. Okay, so now I can take the second partial with respect to y. So I'm looking at this thing and taking the partial with respect to y. X is a constant, so it doesn't affect the minus x. This part needs the chain rule. So derivative of sine is cosine. Inside stays the same times the derivative of the inside. X is the constant coefficient, so that comes out. And then the derivative of this with respect to y is plus 12y squared. Okay, so x times x is just x squared, so you get minus x squared cosine xy plus 12y squared. Okay, so this is example 4